Hello. I'm going to try to explain how we see motion in the stars, and for that we need to understand the Doppler shift. So, if you remember, we talked about a source of light and how it gives out waves, right? And then we looked at sending these to a prism and seeing a spectrum. And if we are looking particularly at a star and maybe say looking at its atmosphere, then we're going to get absorption lines in our spectrum. Okay, so this corresponds to absorption. So we saw how this happens because when you pass this light through a gas and the outside of a star is like, we call it its atmosphere, just like the Earth. So the outer layers of a star are gaseous. So the light coming from lower down in the atmosphere of a star has to pass through the outer layers. And when it does that, then if you remember, there are jumps in the atoms. So an electron will jump from, say, a lower level, maybe the ground level usually in an atom, to a higher level. And in doing so, certain frequencies will be lost, or certain wavelengths. So that gives us like a black line in our spectrum, in our continuous spectrum, where each one corresponds to a particular jump. Okay, so that's just a quick review of the spectrum. So let me erase that. What I want to just talk about now is the Doppler shift. Because this is a very important source of information in stars. So let's say here we are, and we're looking at we'll look at a star, or a light bulb, or whatever you want. Okay, so basically there is a certain wavelength of light. Okay, now suppose here we are again, we're looking at the same star, right? But now the star is moving this way. So what has to happen as this moves, it's still emitting the same wavelength, but it's being stretched out somewhat by the fact that the star is moving. Okay, so I'll say this is the star's velocity. Velocity just means sort of speed in a particular direction. And let's see the other possibility, which is that the star is moving towards us. So it's still emitting light at the same frequency, but because it's moving towards us, I think I'll put that up here, then it gets squished up. So we end up seeing light of a shorter wavelength. So what we find is that if a source is moving toward us, the wavelength of the light emitted becomes shorter. And vice versa. If a source is moving away from us, the wavelength of the light emitted becomes longer. But a shorter wavelength means that the light of that particular wavelength is actually moved in the blue, towards the blue end of the spectrum. So let me write, the light appears more blue than it should be, let's say. Okay, so it should be in the sense of what would be the wavelength if the source wasn't moving. Okay, so let's just see what does that mean in terms of the spectrum. So say we're looking at a star. Okay, well, let's have a look at, I don't know, say this is element X. Okay, I don't know. We're not saying it's any particular element. So, so let's see, which way do we usually write this? This doesn't really matter. Okay, so let's say this is red, and this is blue. Okay, so what I'm going to see if I have a source moving towards me, source approaching, is that the lines are shifted to the shorter end of the spectrum, which is more towards the blue end. So this line becomes here. This line is moved down by the same amount, and this, and this. So each of these lines gets shifted. So we see, what we see is a blue shifted spectrum. So in this situation, we're going to get a blue shift. And in this situation, now the lines are going to be longer. So in this situation, we're going to get a red shift. So maybe I'll put it right here. Okay. So in this situation, this line will have moved to the right. It's not any more red, by the way. It's just in the red end of the spectrum. And this will have moved to the right. So this is a red shifted spectrum. So this is very important for observing stars and galaxies and so on, because we can see, if we know there's a certain element in a star, say we know there's hydrogen, which we do usually, then we can see where are the hydrogen lines. Are they shifted to the left? Are they shifted to the right? Are they in the right place? Okay, so we can actually see sometimes the whole spectrum can be shifted, is shifted one way or another, not just the hydrogen lines. So how does that help us? In what situation would we see this? Well, we would certainly see it, say, if we're looking at the galaxies. We can tell whether a galaxy is moving towards or away from us. One very helpful situation, one situation where this is very helpful, is a binary star system. So suppose we are right here, and now I'm going to put in a binary star system over here. And these stars are actually orbiting around their common center of gravity. So this means there's two stars in one system. Not all that uncommon, in fact very common. So looking from here, this star appears to be moving towards me, right? This star appears to be moving away from me. So the light in this star is going to be, if it's moving towards me, it's going to be blue shifted. In this star, which is moving away from me, the light is going to be red shifted. So in the same spectrum, oops. While they're in this state, a single line may actually be shifted into two lines, because one is from one star and one is from the other. So when they're in this situation, right, this is moving towards me and this is moving away from me, then I'm going to get this. But there is a situation also where they are neither moving toward or away from me, because this is moving this way and this is moving this way. So from the line of sight, the movement is perpendicular to the observer. So when we're in this situation, there's no redshift or blue shift. So I will see a line here, I'll see a line here, and I'll see a line here. This is what we call a spectroscopic binary. Can you see that? Oh yeah. So what you do is you look at this star. You may not see it as a binary star. Some stars are close enough and your telescope may be small enough that you haven't been able to resolve it, right? But what you might see over a period of time is these lines sort of separating into two and then coming back and then separating and coming back. And that is an indication that you're looking at a binary system. Okay, can we see how that works? So this actually gives us like a huge amount of information that it would be very difficult for us to get any other way. It's really, really helpful to have this Doppler shift and to see the Doppler shifted spectra.